Hi, welcome to Hannah, Abraham, and Jessica Dae's project on spectrometers. Our project is specifically on optical spectrometry, which involves measuring which wavelengths an object absorbs or reflects to determine the makeup of the material.
Before we start with our spectrometer and the demonstration and construction, let's go over the physics of why a spectrometer works in the first place. Spectrometry centers around the physics topic of wave optics. This basically follows the wave theory of light, meaning that light is made up of and travels in electromagnetic waves rather than rays. The principal idea behind spectrometry and one part of wave optics is the emission of light from elements. Each element has a unique set of energy levels that electrons exist on. Two examples are shown here. When an electron moves energy levels, they emit or absorb a certain amount of energy, depending if they're moving up or down, that corresponds with a certain wavelength of light, meaning that each element also has a unique set of wavelengths of light they are able to absorb or emit. So, if we can identify what wavelengths they are, we can identify the element itself. Now to get into how a spectrometer actually works. This will be a model of a very basic spectrometer. First of all, there must be a source emitting light, which in this case is a candle. The wave of light leaves the source and hits a diffraction gradient, consisting of several tiny ridges that reflect different wavelengths of light at different angles, so they will be separated. This is not unlike what a prism does in creating a rainbow from white light. Then, the separated light hits a detector, usually connected to some sort of computer or receiver, that then records and identifies the wavelengths. Based on this data, the element emitting the light can be determined. Later on, when we talk about the applications of the spectrometer we built, we'll discuss how it can be used with absorption rather than emission.
Now let's get into the history of spectrometry. The first scientific study of spectrums was done by Sir Isaac Newton in 1666. Newton pointed a ray of light at a prism and saw a band of colors projected onto the wall. He added a lens and was able to split the colors into a spectrum. That was the birth of spectrometry. Later, in 1814, Joseph von Fraunhofer tried experimenting with single-slit diffraction, which is using a narrow slit to create spectral lines with wavelengths of light. Spectral lines are dark or bright lines resulting from the release or absorption of light and are used to recognize molecules and atoms. Fraunhofer is credited with creating the first spectrometer, which is essentially a prism marking wavelengths of light. Developments continued in the mid-1800s when Gustav Kirchhoff recognized that each compound has a unique spectrum, which could help determine its chemical composition. Technology advanced even more, and spectrometry expanded into other branches of science, like astronomy and chemistry. Fraunhofer used spectrometry to study the makeup of stars, and scientists Bunsen and Kirchhoff used it to analyze the composition of elements. Advances in photographic film led to the development of a more accurate spectrometer. It allowed scientists like John F. W. Herschel to be able to study the ultraviolet section of the spectrum. Spectrometry was used to outline the structure of an atom, enhance cancer research, and improve forensics. Materials needed are a black VHS box, scissors, X-Acto knife, duct tape, black card paper, a DVD-R, a USB webcam, and a computer with web connection.
First off, you need to cut off the VHS snubs on the inside of the case. This is to make sure that the inside is as smooth as possible and that there is less interference from the light when it enters it. Next, carefully and precisely fold a piece of cardboard and then cut a less than 1 mm slit in the folded over end of the black card. The slit should be at least 5 cm from the card edge. And then, place the black card in the VHS case and cut an opening in the VHS case to expose the slit. This is where your light will enter the spectrometer. Now moving on to the webcam. First, you need to prepare the webcam by removing the clip section so that the camera will sit as flat as possible. The webcam needs to not have an infrared filter on the inside. This can either be done by removing the filter or getting a webcam that simply doesn't have one in the first place. Next, you must align the webcam with the slit and secure it to the case using electrical or duct tape, making sure that the beam of light that enters the case through the slit will hit the webcam camera. Now it's time to add the DVD that will serve as your holographic diffraction grating. First, cut the DVD keeping close to the outer edge. remove the shiny layer and the plastic from the back of the DVD and cut a small piece from the clear layer. Next, secure that DVD piece in front of the webcam lens using either tape or glue. It is preferred to use hot glue since something like super glue will create more fogging of the DVD, but really any strong adhesive will work. Now it's time for just the last few steps of building the spectrometer. Carve a small notch in the VHS case for the USB cable to connect the webcam on the inside and a computer on the outside. Then, add tape to block any gaps in the case once it is closed to prevent any light leaks from getting inside the dark interior. Lastly, all you have to do is use an online program like Spectral Workbench to capture and calibrate the spectra you receive when capturing the wavelength using the webcam inside your spectrometer.
In this demonstration, we are shining a light through water that has red coloring in it. We aimed the spectrometer at the light for a few seconds, and once we saw a desirable output on the computer, we saved it and added it to the Spectral Workbench database, which is a collection of spectra that other people have uploaded to help detect materials based on spectrometry. When we look for a match in the database, we see that an incandescent lamp spectra shows up, which means that part of their makeup is very similar. It is similar to the red water because the absorption spectrometry shows high blue and green values compared to the red in both spectra.
Okay, now we're going to get into the practical applications of spectrometers and add a few more specifics about our own. Our spectrometer is an optical spectrometer that uses absorption spectroscopy. This may sound complicated, but an optical spectrometer is just the same type we explained with the basic diagram earlier in the video, and absorption just means it registers the light absorbed rather than emitted. Elements absorb the same wavelengths they emit, so it's still relatively the same principle. In order to further compare emission and absorption, here are their spectrums. The top box here will be an emission line spectrum, and the bottom box will be an absorption line. You're probably more used to seeing the emission spectrum, which is simply lines of light varying in wavelength. The absorption is extremely similar, except it consists of nearly the entire spectrum of light, with just a few lines missing. The missing lines are what has been absorbed by the element, and can be used in the same way as emission lines to figure out the element absorbing them. This was seen in the project demonstration video, when the contaminated water absorbed some of the light shown through it, and we could tell what elements were in it. One common application of a spectrometer is in studying astronomy, specifically the chemical composition of celestial bodies. Since we can't exactly fly to a star and get a sample to see what it is made of, we can use a spectrometer and emission spectroscopy to see what elements are in it and what elements are emitting the light of a star. Another application is the one shown in the demonstration, contaminated water. These are two samples of water, one contaminated and one not. Though we can't see the chemicals in the second using the naked eye, spectrometry can determine what each sample contains. Shining light through them and then into a spectrometer can reveal what elements are in it and if it is safe to drink. This uses absorption spectroscopy, as you are measuring what wavelengths of the original light are absorbed. This is a very important application, as it can be used in many situations to test drinking water. There are obviously many other applications and times when it would be useful to know what element something is made of, but we couldn't possibly cover it all. So thank you so much for watching, and we hope you enjoyed our project and video.